The European Union has launched its COVID vaccine rollout with plans to vaccinate more than 450 million people. The first 200 million doses are from Pfizer. NBC News chief global correspondent Bill Neely has a look at how the rollouts are going outside the U.S.
In the global race between injections and infections, millions have now been vaccinated against the COVID virus. In China, where it first appeared, more than 20 vaccines are in production, several approved and now being sent abroad.
Welcome to our SI330 Final Project. The COVID-19 pandemic has been affecting people around the world for over a year now. It has infected almost 150 million people and claimed more than 3 million lives. Given we are now seeing what is hopefully the light at the end of the tunnel, with vaccine rollouts moving steadily in the United States and many nations around the world, we thought it would be interesting to examine vaccine rollout data in the countries which seem to be most successful. For our purposes, we define most successful as the ability to administer as many vaccinations as possible in the shortest span of time. As of April 12th, the CDC reported that about 22.3% of United States citizens have been vaccinated. This number is higher than many countries and lower than some as well. In our project, we utilized Python and SQL and multiple accompanying packages to analyze hundreds of countries around the world to see the correlation between a few specific factors and the rate at which these countries have managed to vaccinate their citizens. Our goal is to identify which factors of a country have the highest correlation with the fastest rollouts, and with that we hope to predict which type of countries will be able to vaccinate their populations effectively in the future under similar circumstances. We feel that this is quite important given the concern over variants to the virus and the possibility of COVID becoming a permanent challenge to be addressed yearly, like the flu or common cold. For example, we know by now that the variant, now known as B.1.1.7, quickly became the most common version of the coronavirus in the United Kingdom, accounting for about 60% of new COVID cases in December of 2020, according to a Johns Hopkins medical article. Therefore, it is not unwise at all to be preparing for the possibility of a challenging future. We think that our data should show which factors countries which have been less successful with their vaccination process should strive to adopt moving forward. Throughout this video, you will see the sources we retrieved our data from, how we processed it, how we visualized and analyzed the data, and how we tested it. We hope you enjoy learning about the work that we put in.
Before we get into the data cleaning, manipulation, and analysis, it is important to give an overview of what data we are using. We use Kaggle.com to find two separate CSV files, which we then converted into Pandas data frames. Kaggle is a subsidiary of Google LLC and grants users access to a community of data scientists who are finding and publishing datasets and other web-based engineering products. The first file is a 2 megabyte file titled COVID-19 World Vaccination Progress, and it contains vaccination data by country, starting as early as each country's first reported vaccine distribution. This will be the temporal aspect of our data analysis because we will examine vaccine rollout and quantity distributed over time. For example, the earliest date in the file is from the United Kingdom on December 13, 2020, reporting the use of the Pfizer and AstraZeneca vaccines. We will compare these initial numbers to the numbers that we are more recently seeing in countries across the globe to show the growth in vaccinations over time. There are 197 countries in the world, so these will be the 197 records or columns that we will be looking at. However, we will also narrow this quantity down by a cross-analysis with the variables in our second CSV. And the second CSV is a 37 kilobyte file, and it is titled Countries of the World. It contains general statistics from all the countries in the world. The variables we considered most relevant to our hypothesis and vaccine rollout in general include GDP per capita, population density, and rates of phone access. First, we found GDP to be an important indicator because GDP represents the performance of a country's economy in terms of imports and exports, which can also have a correlation to salaries, wages, and consumer spending. So I guess further, we are interested in GDP to see if there's a potential direct correlation between a high GDP and a high vaccination rate. The next thing we're examining is population density, and this is of interest to us because this will provide us with a baseline to compare the vaccinated population to. Lastly, we are considering rates of phone access and in terms of phone ownership per 1,000 people because we believe that key information regarding vaccine availability and location will be spread through digital technology.
Before we added both CSV files to DeepNote, we imported Pandas, NumPy, Penguin, and Matplotlib as they were libraries we would need to successfully process and analyze the data. Then, we read both CSV files into the notebook as Pandas databases and labeled the COVID-19 World Vaccination Progress database as vaccination and the Countries of the World database as facts. Now, we'll walk through the calculations and the data manipulation that we conducted on the vaccination database. Our first goal was to find the total vaccination data for each country. We began looking at the total vaccinations column and dropped all the NAN values. This step was conducted to make sure that we were working with the most relevant data, which would ultimately ensure that our conclusions were accurate. Next, we grouped by country and applied a max function to return the maximum total vaccinations from each country. Then, we moved into working with the facts database and did some basic data cleaning by stripping excess whitespace in the country column and formatting the capitalization of the columns. We also isolated the 5 columns that we were most interested in from this database, including the 3 variables that we would use for further analysis and calculations, renaming this as facts.df. This step was so that we would end up with 2 data frames, each only containing key variables and contextual data to merge on. We used a left merge on the country column to keep the columns from the vaccination data frame. We did this merging a function called createMergeDF, which took in the 2 data frames we created, vaccination and facts.df, the index version of the facts. Our final data processing task consisted of turning the original databases, VacDF and facts.df, into SQL databases. To bring the 2 together, we did a left join on VacDF into the facts.df database on country. We then selected to return the country column in another column which was renamed as % of population full vaccinated, that calculated the people fully vaccinated divided by the population and multiplied by 100 to give us the percentage of people vaccinated by country. To find the countries with the highest percentage of people vaccinated, we ordered by the % of population full vaccinated column in descending order, limiting the number to 10. As mentioned in our motivation and data sources section, we created visualizations to depict any relationships or correlation between GDP per capita, phone access, population density, and vaccinated population. I'll now move into talking about each of the 4 visualizations and 3 t-tests that we created. First, I'll talk about this visualization that we created to analyze the relationship between GDP per capita and total vaccinations in countries. More specifically, we analyzed the 5 countries that had the lowest GDP and the 5 countries that had the highest GDP. We created a t-test to analyze if these relationships were consistent with our original hypothesis. The countries that have a higher GDP will also have a larger vaccination population. Our test returned a p-value of 0.008. A p-value of this size, meaning less than 0.05, tells us that we should reject our null hypothesis. In this case, our null hypothesis was that there is no relationship between GDP per capita and vaccinated population. Because we are rejecting this hypothesis, we can conclude that there is a relationship between GDP per capita and vaccinated population. However, it is important for us to recognize that this conclusion may have its biases. As shown by our visualizations, there are countries that have a low GDP yet have a larger vaccinated population. This may be due to difference in overall population because, for example, India, which has a low GDP, has a high vaccinated population in comparison to Luxembourg, primarily because India has a greater overall population. The next visualization was created to show the relationship between population density and vaccinated population. Based on these graphs, we can see the countries that have a high population density and a large vaccinated population, like Singapore and Hong Kong, or countries that have a low population density but a large vaccinated population, like Norway, or countries with a low population density and a low vaccinated population, like Canada. Our third visual and the corresponding t-test represents the relationship between phone ownership and the vaccinated population. In order to apply this t-test, however, we had to conduct some basic data manipulation. Basically, the values in the phones per 100 column were separated by commas and were objects. We had to use the .replace function to cast these objects as 4. Applying logic similar to what we used in the first visualization, we can conclude from our t-test that there is a relationship between phone ownership and vaccinated populations. Our fourth and final visualization shows the most popular vaccines across the world. Our percentages add up to more than 100% because many countries use multiple vaccines.
With all programming, it is very helpful to have test functions to ensure that there are no flaws or bugs within your work. In our case, with frequently updating data and complex processing and cleaning functions involved, it is especially important. As you know by now, the 3 main data points we were looking at were GDP per capita, population density, and phones per thousand. We therefore created a few crucial functions for each one, which allowed us to compare those values to total vaccinations. In order to ensure these functions were working properly, we have some tests to run on the output of those functions. The functions which we test are create merge data frame, GDP in vaccine, density in vaccines, and phones in vaccines. The first one to test was the function which merged the country data frame with the vaccinations data frame, because this was central in our ability to compare data across multiple sources. We began by making sure that it was returning a data frame at all. Then we wanted to confirm that the total vaccination column contained float 64s, which we needed for the calculations we were making. Next, we made sure that the new merged data frame had a number of columns equal to the sum of the number of columns in the 2 originals, minus 1 for the total vaccinations column. Finally, we made sure that every country in the merged data frame could be found in both previous ones so we could get useful data for every row in the merged one. The next 3 test functions are all quite similar, and they follow a distinct pattern. GDP in vaccine, density in vaccines, and phones in vaccines all return 2 values. The first value is the lowest 5 countries sorted by the specified value, and the second is the highest 5. Our test function first tests to make sure that every value in the lowest 5 is smaller than every value in the highest 5. If this was failed, we knew something was clearly going wrong above. Then, using internet sources like statista.com and more, we confirmed that our lowest or highest found is actually accurate. In a few cases, the lowest or highest isn't exactly correct because our data pertains to countries that have available vaccine data. So we also use the internet sources to ensure that certain data is close enough to still utilize for our analysis. An example of this would be Luxembourg. Luxembourg shows up as the nation with the highest GDP per capita, but is actually number 3 in the world because Qatar and Macau do not have available vaccine data to work with at the moment. Overall, our tests help us to understand that our processing functions were working as intended, but there are certain limitations involved when some data just isn't readily available. We still believe that we went about executing our goal as well as possible with the given data available.
Now moving on to our conclusion. Through this project, we learned about more than just vaccination rates in countries. We learned that sometimes it might be harder to draw relationships between 2 variables than initially anticipated. Prior to really working with the data, our group created a hypothesis to predict the relationship between our main variables of interest, which were GDP per capita and accessibility of phones. We believe that countries with a high GDP per capita and a high quantity of phones per 1,000 people would have the highest vaccination rates. Some of our prior experience working with predetermined data and running statistical tests from SI330 and other courses had us hopeful that we would see 2 perfectly representative graphs of causal relationships. However, this project taught us that although this outcome is ideal, it's not always possible. Sometimes seeing a direct relationship between 2 variables requires a lot of data cleaning and manipulation, and other times these variables are influenced and affected by too many outside factors that a relationship cannot be reliably drawn. With vaccine data changing every day and some countries not having access to proper reporting techniques, despite how hard we tried, it's hard to be sure that we were working with the most reliable and up-to-date data. Our experience in realizing this, specifically with vaccinated population and GDP per capita, has helped us also develop an understanding of the complexity of vaccine rollout in general. There are so many factors that affect a country's access to the vaccine, with many of these factors also having influence on one another. For example, GDP can affect phone access, which can reflect the technology advancements of a country, and with vaccinated population being a function of overall country population, we can see a lot of unintentionally skewed data. Through this project, our group was able to apply our knowledge of material covered in lecture while also gaining real-world experience in experimenting with causal relationships amongst variables. Thanks so much for listening.